Welcome to video number 34, folks. Today we're going to be talking about, well, today we're talking about several things, but in this video we're going to talk about the Earth's magnetic field. Remember, we've got the water is called the hydrosphere, right, that surrounds the Earth. There's also something called the lithosphere, just underneath the crust and so forth. But now we had the atmosphere above that, and now we've got above the atmosphere, we've got the magnetosphere, known also as the Earth's magnetic field. Now, you've experienced the Earth's magnetic field anytime you've looked at a compass. The compass needle always swings to the north. And so we're surrounded by a magnetic field. And we've all, you've had magnets. Here's a couple of bar magnets, iron, really bar magnets. I'm not sure. They're probably too dark for you to see very easily. Show them up against this, right? These couple little magnets here. They're quite dark. But you know how magnets work. You can flip them one way and they stick together. These are known as bar magnets because they're long. You could also have them bent, into a horseshoe shape or something like that. But these are known as bar magnets, okay? These two magnets here. Again, probably too dark to see them well, but that's what we got. A couple of bar magnets. If you flip them the other way, they push apart from each other, but if you flip them this way, they pull together and stick. So the point I want to make is that the Earth acts like it's got a big bar magnet inside of it. This yellow thing I've drawn here is kind of like one of my little bar magnets. Now, the Earth doesn't actually have a great big iron bar magnet sitting inside of it like my drawing here. But from the surface, it seems like it does. Okay, the magnet is really sort of, the Earth's magnetic field is due to iron, okay, much like this, but it's not shaped like this. But I draw it there on the Earth to show you that there is sort of, it behaves as if there's a big bar magnet inside. And that big bar magnet is not aligned perfectly with the rotation axis of the Earth. It's tilted by about 5 degrees relative to it. So the north magnetic pole of the Earth is not actually at the north geographic pole. When we talk about the north pole of the Earth, right, we typically think about the north geographic pole, the spin axis, the point at which the spin axis pierces the Earth at the North Pole. But the Earth's magnetic pole is in northern Canada, okay? It's a little bit northwest of Hudson Bay, so that's because of this 5-degree tilt. And the Earth's south magnetic pole is on the edge of Antarctica, just south of Australia. So there is a tilt involved. But what I need you to know is that the Earth has a magnetic field, and it behaves as if there's a big old huge bar magnet stuck inside the Earth, tilted about 5 degrees relative to the Earth's spin axis. Some planets have huge magnetic fields, some of them have small ones. The Earth has a large one when compared to the other 3 terrestrial planets. But its magnetic field is very small compared to the Jovian gas planets in the outer solar system. Okay, so there's that. Now, what happens is, where's my pen? Here it is. We talk about this in the space surrounding a magnet. We say there's a thing called a magnetic field. Okay. Like, for example, where I'm standing right now and where you're sitting right now, or standing wherever you happen to be, there is a magnetic field in that space all around you that is created by the magnet down in the Earth's core. So you are in the space around that core, and that space is filled with a magnetic field. And we draw that magnetic field typically pointing from the south to the north like this. Okay, these are known as magnetic field lines. Draw on the other side too. They point from the south to the north. And you'll see them oftentimes drawn like that. Okay, so out here in space, and they also run across the surface of the Earth where we live. Okay, and that's the magnetic field that our compasses respond to when we're just standing around on the surface of the Earth. Okay, So it fills the space around the Earth. It gets really intense near the poles, and it's less when you're far out. But the field, of course, surrounds the entire Earth. And you can't taste it, you can't feel it, you can't smell it, but it's there. And it goes way, way, way out beyond the Earth's atmosphere as well. So it goes thousands of miles out into space. The arrows indicate the direction a compass would point if you placed it at that location. Okay, so if you were way out in space, you know, a third of the way to the moon, and you held a compass right here, the magnetic field would point. The compass would point that way. Okay, so that's what these arrows tell you. They tell you the direction a compass would point if you held it at that location. They point from the Earth's south pole to the North Pole. Okay, so the Earth's magnetic field surrounds the globe. Let's see. Oh, that angle is actually more like 11 degrees, not 5 degrees. I was thinking of a different angle. Not sure what I was thinking of, actually. Actually, I do know, but I'm not sure why I was thinking it. This angle is more like 11 degrees. All right, what else did I want to say about this before I move on? Okay, so the Earth's magnetic field exists, and it's really good for us that it does. For sure, because the sun's out there, right? Here's the sun. You'll recognize the sun anywhere. There's the sun. And the sun creates not just light, which is really good for us, but it also creates something known as solar wind, which streams out in all directions from the sun, including the direction of the Earth. And this solar wind contains charged particles in the form of protons and electrons. Okay? Not connected to atoms, just plain old protons and electrons. Okay? These are charged particles, and there's also other stuff, but for our money, what we're interested in are these protons and electrons. Okay? And they're moving really fast. And you know what? If it were not for our Earth's magnetic field, they would come all the way down to the surface and be very damaging to our bodies. If we could get rid of the Earth's magnetic field right now, everybody would start getting cancer. It's true, because these charged particles would strike our skin. We start getting skin cancer and a number of other cancers as well. We get very unhealthy. All kinds of health issues would occur if we didn't have our magnetic field. It, like certain layers of the atmosphere, is protective. Outer space is a harsh place. We used to think outer space was dangerous because what was not there, like air. But the truth is, space is dangerous because of what is there. And in our neighborhood, that means these very fast protons and electrons, okay, from the solar wind. Very dangerous. And that's what makes being out in space very dangerous. The only people who have escaped our magnetic field and gone beyond it are the astronauts who have gone to the moon. Whether or not they walked on the moon, those are the ones who have been exposed to this radiation. This is also known as radiation sometimes. These charged particles, I'll put it that way. And so they've been exposed to that, and it's very dangerous. So these charged particles don't make it to the Earth. They get trapped in regions known as I'll make these pink. There's two major ones. There's one that's lower down like this. Looks like in the drawing it looks sort of like a couple of kidneys. But remember, this field wraps this is just like a slice of an apple, okay? It goes all the way around, behind the board, in front of the board, and all this. This is just a cross-section of it. So down here and out here, we have these two big regions. So these are known as the Van Allen belts, these pink regions. And remember, they're not just the shape of kidneys. They're the shape more of weird-shaped donuts. They wrap all the way around the Earth. Okay, And the outer one contains mostly electrons. Remember, they wrap around the Earth. Okay, they're belts. No, I didn't write this. The Van Allen belts. Okay, the outer one contains mostly electrons. The inner one contains mostly, not all, but mostly protons. Okay, because the differing masses of those two particles, the protons are more likely to go further, go right through the outer belt. They're carrying so much momentum. But anyway, they fill up a little bit differently, and so we have these charged particles, and these charged particles fill up these regions known as the Van Allen belts. There's two major ones, like I said, way above the Earth's atmosphere. The astronauts had to go through them on the way to the moon. It's dangerous because they're filled up with these charged particles. But the point is that they get trapped in these belts and then don't make it all the way down to the Earth. That's what's good for us. Okay, they get trapped in these belts that surround us. They're sometimes called the Van Allen radiation belts. I don't know if your book calls it that, but that's another term you hear, is Van Allen radiation belts. Now, every now and again, we get more solar wind than usual, and we'll talk about the sun next week and why that happens. Sometimes we get a lot of solar wind, and sometimes we get only a little. These days, we're getting only a little. Here in 2020, we're getting relatively little solar wind. But sometimes these belts fill up, and they spill over, and charged particles fall down to the poles. What I mean by this is these belts, as they collect during those times when the sun is very active and we're getting more and more and more solar wind, these belts act kind of like bottles. They trap the charged particles like bottles trap water. Okay, but when there's a lot of incoming particles, these belts leak, they overflow. And when they overflow down into the poles, and charged particles fall down towards the poles. These protons and electrons stream down to the poles during regions of high solar activity. And that creates what is known as the aurora. I don't know if any of you have ever seen the northern or southern lights, but I envy you if you do, because I never have, despite having a couple of opportunities and did not know it until later. But the aurora borealis in the north, the northern lights, borealis, and aurora australis in the south. Again, those are during regions of high solar activity. Lots of protons and electrons come and get trapped in the Van Allen belts, but there's so much coming in that they overflow, and when they overflow, they always overflow and such that the electrons and protons fall down to the poles, and when they do, they ionize the particles in the atmosphere, and that creates the lovely glow that you see at the north and at the south, and you're more likely to see them the further north you are. They occur a little bit even when the sun is not particularly active. But when they're super active, sometimes you can even see the northern lights from way down here in Georgia. Okay, so that's it for the magnetosphere. Anything else to say? No, I think that's it. Okay, next up, we're going to talk about the tides. You might not have ever seen the the aurora borealis. Okay, but you've all seen the tides. I assume you've all been to the beach at some point and seen the water almost twice a day, up and down, up and down. Tides are next.